Hello everyone. In this video, I'll go over problem number 17 from chapter 4 in the textbook. What I'll do is I'll quickly go over the formulation and then I'll show you how to solve this in Excel. This is a very common kind of problem called make or buy, where you have to decide whether you want to manufacture something yourself or you want to buy it from, say, a subcontractor. Right? So Frandex manufactures, assembles and rebuilds material handling equipment in warehouse and distribution centers. One product called the LiftMaster is assembled with 4 components: a frame, a motor, 2 supports and a metal strap. Right? Frandex production schedule calls for 5,000 LiftMasters to be made next month. So you need 5,000 LiftMasters, so 5,000 products. And Frandex purchases motors from an outside supplier. So manufacture of motors is not part of this problem. But the frames, supports and straps are either manufactured by the company or purchased from an outside supplier. So the manufacturing costs for making a frame, a support and a strap are given here, and for making purchasing from the outside are also given here. Right? Now 3 departments are involved in the production process. You have a cutting department, a milling department and a shaping department, and this is how many hours it takes to cut a frame, mill a frame and shape a frame, and a support for cutting, milling and shaping, and straps, cutting, and there's no milling required, just cutting and shaping. And this is the total capacity in hours that are available for cutting, shipping, and milling and shaping. Right? So formulate and solve a linear programming model for this make or buy application. How many of each component should be manufactured and how many should be purchased, right? So that's the decision that we have to make. Now, a couple of things I want you to notice is that if we have to make 5,000 LiftMasters, right, which means that we need 5,000 of all the individual parts, or maybe more, right? So each LiftMaster requires 1 frame, 1 motor. We don't have to worry about the motors coming from outside, but it requires 2 supports and a metal strap. So if we are making 5,000 LiftMasters, we have to make 5,000 frames, 5,000 straps, and 10,000 supports, right? Because each LiftMaster requires 2 supports. So that's what we need: 5,000 frames, 10,000 supports, and 5,000 straps. So that's what we need. We can make some in-house based upon the times that's available to us, or the rest we buy from outside. The question is, we have to figure out how much we are making in-house and how much we are buying from the outside, right? Now, when you're making inside, the time that's available has to be properly allocated to the different departments, and make sure that we write the constraints properly to do this. So let's set this up as a problem and solve it. Okay, so I'm just going to move it down a little so that the data, I can see some of the data here, right? So I'm going to say FM is number of frames manufactured, SM, number of supports manufactured, right? So as usual, we're going to set up our decision variables, and STM is number of straps manufactured. Well, you know, just call it TN. TN is number of straps. So dollars, number of manufactured. All right. Now, you'll notice that we are only given cost values, the cost for manufacturing it itself and the cost for purchase, which means that this is going to be a cost minimization problem. There is no profit values given, the sales price or anything like that. So given that it's a cost minimization problem, a couple of things will help us out. There's also no cost given for the time itself. So we are assuming that all of that is included in these cost numbers, right? So apart from this, we also need FB, this will be number of, let me just copy this over. I don't need to rewrite the whole thing again. I'm just going to call them FB, SB, and TB. TB, that's unfortunate. Number of frames bought, right? This is how much you buy from outside. SB is the number of supports that are bought, and TB is the number of straps that are bought. Okay. So those are 6 variables. How much do we make? And how much do we buy, right? Now, given the demand constraint, so we can before that, let's set up the objective function. The objective function is to minimize cost minimize cost, which will be, we know the value, so it'll be $38 times the number of frames that are manufactured plus 1150 times the number of supports that are manufactured plus 650 times the number of straps that are manufactured plus, oops, then you have $51 times the number of frames that are bought plus $15 times the number of supports that are bought plus $750 times the number of straps that are bought, right? So that's the total cost. These are the only costs given to us. We're not given labor costs, we're not given sales price or anything like that. So based upon the costs that are given to us, this is the total cost of either manufacturing or buying, and this is what we want to minimize, right? Now let's write the constraints. So for constraints, there are two types of constraints. One first will be the demand constraints. So we say that the total number of frames that are manufactured have to be 5,000, right? Because we need 5,000 frames in total. Now, total number of supports that are manufactured, that we get either manufacture or buy. So this is the total number of frames either manufactured or bought. Total number of supports manufactured or bought have to be 10,000 because we need 2 supports per. And then the total number of straps that are either made or manufactured, made or bought is 5,000 again, right? So we have demand constraints. Apart from this, now we have the manufacturing constraint. So let's begin with cutting. Down a little so I can get all the data in. So let's write the cutting constraint. So the cutting constraint will be, it takes 3.5 hours to cut a frame. So this is only for manufacturing. Buying, we're just buying fully made frames from the outside. 1.3 hours to cut a support and 0.8 hours to cut a strap. So this is how many hours we need to make all the frames, how many hours we need to make all the supports, and the number of hours we need to make all the straps. And this cannot exceed 350 hours, right? And then the same goes for milling, 2.2 for the frames, 1.7 for the supports, and nothing for straps. So straps don't need milling, so this is 420 hours. Shipping is 3.1 frames plus 2.6 hours for support and 1.7 hours for straps. And this cannot exceed 680 hours, right? Okay, good. So with this, we have our 6 constraints, and that includes everything, right? So 5,000 lift masters are made. We know that it's 1 frame, 2 supports, and a metal strap. Blah 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 blah. This is the cost of manufacturing. This is the time that's available, and that's pretty much it. So that's our formulation right there, right? So we have 6 decision variables and 6 constraints, right? 3 of them less than or equal to, 3 of them equal to, and then we're trying to minimize the cost right here. Okay. Now, these equal to constraints that we have, we can write them as greater than or equal to constraints. It won't matter because we are minimizing cost. We're going to do the bare minimum anyway, right? Okay, so let's put this into the solver and solve it. Right. So we go. Decision variables, right? So we have FM, SM, and TM for frame support and straps, manufactured, then FB, SB, and TB for frame supports and supports and straps that are bought from outside. And of course, we have the left-hand side, right-hand side, the usual. Go. So these are my 6 decision variables right there. Let's write the objective. Right? So the objective, that's the cost. Let me just like that. Okay, good. Okay, so we have $38. $11.50, $6.50, $51, $15, and $7.50. Right? So we have the objective function numbers. The objective function will be right there, right? So I'm going to color that afterwards. Let's write the constraints. So we got three demand constraints. I'm going to say demand for frames. Demand for frames. Then demand for straps. Supports and demand for straps, right? So we'll say demand for frames is 1 there plus number of frames made plus the number of frames bought has to be equal to 5,000. Number of supports made plus the number of supports bought has to be equal to 10,000. And number of straps made and the number of straps bought has to be equal to 5,000 once again, right? Next. Now we write the time constraint. So first we'll write cutting, milling, and packaging. Is it packaging or something else? Cutting, milling, and shaping. I'm so sorry. It's not packaging, shaping. All right. So cutting is 3.5 hours. 1.3 and 0.8. 2.2 and 1.7 and 3.1, 2.6 and 1.7. All of these are less than or equal to constraints. Wait. Oh yeah, I messed up. Cutting and shaping, and this is 350 hours, 420 hours, and 680 hours. All right. Now I am all set up. Now let's write the sum product formula of the coefficients and the decision variables. So the decision variables obviously are going to be absolute references. Okay, let's go to the solver and solve this. Huh? Okay, so cost minimization, minimize, changing variable cells, there's 6 of them. Three equal to constraints first. Add 3 less than or equal to constraints. And I think I'm gonna mess up. Oh yeah, no, I didn't mess up. I thought I wrote all of them as equal to. Okay, right. So equal to constraints, less than or equal to constraints. There are no binary constraints or anything. So now I'm going to click on solve. And there you go. So according to this, apparently it makes a lot of sense to buy. So we are only making 100. Hang on, did I do cost minimization? Yep, we did. Okay. All right. So the optimal solution is $441,200. That's the cheapest you can do it. Where you buy 4,900 frames, all the 10,000 the sides and 5,000 straps, all of them from the outside. All we're doing is manufacturing 100 frames, and just to manufacture those 100 frames, it takes 350 hours because it's 3.5 hours right here, right? So takes up 350 hours here, and that's the maximum that you can do. So that's basically what we are doing here, right? So in this case, we are buying most of what we need, but yeah, that's basically it. Hang on, did I do any minute to hour conversion or something? Let me just quickly look something up. Capacity is 350 hours. Time in minutes. You know what? I knew this was time in minutes. I knew I was messing it up. Okay. So this is 3.5 minutes. So all the capacity is in hours, and I got to change that. Yeah. See? I knew it was in minutes. I don't know why I left that. So let me first go change it here. This is 350 hours times 60 minutes, right? So 350 times 60 is 21,000. So it'll be 21,000. We are going to do everything in minutes. It makes it much easier. Times 60. Actually, right? Which is 25,200. And finally 680 times 60 will be 40,800. Okay, that makes so much more sense. I knew I was missing something. 21,000, 25,200. Okay, with this, let's go back to solver and click on solve. Okay, looks like we ended up with some non-whole number, so we're going to fix that in a second. But approximately, so this is the answer. So let me go back, solver, add a constraint that all of these numbers, they all have to be integers, right? There you go. Just rounded it up. So we are making all the 5,000 frames. We are making 2,692 of the supports. We are not making any of the straps. All the straps are coming out, because if you notice, the cost of making a strap is 650 and cost of buying a strap is 750. That's not that different, but cost of making a frame is $38, while the cost of buying a frame is $51. So that's a lot. It's much different. Right. So the objective function is 368,078, and that's the optimal solution. Right. Okay. So that was an example. Now it did turn out to be a integer programming problem, but you know, that's just the last step. Otherwise, it's mostly a linear programming problem. Right. Okay. So I'm going to stop here. If you have any questions, feel free to email me, and good luck on your midterm. Right. Take care.